This is a unit on multiple regression, and for reasons which I guess I don't really recall, I put frogs on a lot of the slides for this unit. So if you really like frogs, you may really enjoy this unit. And if you don't like frogs, well, hopefully this will not diminish your love of multiple regression. So what is multiple regression? So multiple regression is just an expansion of simple regression. And simple regression is what we were doing in our previous unit. In our previous unit, we were looking at regression equations that had just one single outcome variable, which we called y, and one single predictor variable, which we called x. And our equations were ones where we said y was equal to an intercept plus a slope times x plus error. And we figured out values for our intercept and values for our slope that would minimize the sum of the squared error. And when we did that, the value for our slope was particularly important because it told us about the relationship between x and y. It told us how well x predicts y. What is the expected increase in y given a 1 unit increase in x? So with multiple regression, we're simply going to add predictor variables. So with multiple regression, we're no longer limited to just a single predictor. That is, we're not limited to a single x variable. We could have 2, 3, 4, or any number of predictors. This example here, I have 3 predictors, 3 x variables, x1, x2, and x3. And as we will see, our regression equations will have a slope for each x variable. So if I have 3 x variables, I'll have my beta 1, which will be my slope for x1. Beta 2 will be my slope for my second predictor variable. And beta 3 will be my slope for my third predictor variable. So taken together, we have an equation that says y is equal to an intercept plus a slope 1 times x1 plus slope 2 times second predictor variable plus slope 3 times x3 plus error. When would we use an equation like this? I have an example at the bottom here. Would be from an example, say I was working with doing psychotherapy for maybe say it was people who were suffering from depression, and I was doing some form of psychotherapy to try to help relieve people's feelings of depression. And one of the key outcomes in that situation would be the client's level of well-being at the end of therapy. After therapy is all done, how much is the client happy and healthy and feeling positive levels of well-being in his or her life? And so we might ask the question, what are things that might occur during therapy that could predict client well-being at the end of therapy? What are the processes that would occur during therapy that might predict client well-being? And I have here 3 possibilities, 3 different predictors that we might want to consider in a study. So here I have x1 is alliance. That is, to what extent does a client feel like he or she has a positive alliance with a therapist? The positive alliance would involve feeling like you and a therapist are working towards the same goals, feeling like you trust a therapist, like the therapist likes you, and like you have confidence in the therapist. All those would be parts of having a good alliance with one's therapist. And presumably, if clients have a better alliance with their therapist, they might do better during psychotherapy, and that might lead to more positive, better client well-being at the end of therapy. Another possible predictor could be the therapist's positive regard. That is, to what extent does a therapist communicate to the client a message of, you are important, I value you, it's important for me to spend time with you, you're a valuable person, and no matter what you do or what you say, I will always regard you as a valuable person. That would be aspects of therapist expressing positive regard toward the client. That idea actually comes from Carl Rogers, who is probably the first psychologist to have a prominent theory of psychotherapy. He developed his ideas a lot in the 1940s. And before that, people did psychotherapy, but they were mostly medical doctors who were trained in psychiatric settings, and they would have been psychiatrists. And most of the psychiatrists doing psychotherapy at that time followed a lot of Sigmund Freud's ideas, or ideas that were related to Freud's, that are sometimes called psychodynamic approaches to therapy. And Carl Rogers was not a medical doctor, but he was a psychologist and was actually one of the first psychologists to pursue a particular unique, non-Freudian approach to doing psychotherapy. Today we know there's probably a lot more to psychotherapy than just expressing positive regard. Carl Rogers' theory is probably overly simplistic, but one of his ideas was the importance of expressing positive regard. Interesting note on Carl Rogers is that he was also one of the first psychotherapists to try to do research on psychotherapy, although he pursued it in a rather unethical way. He decided to start recording therapy sessions, which he did with, at that point they had phonograph records, so he was trying to make recordings onto phonograph records, but initially he did it without the client's knowledge or consent. He actually hid microphones and lampshades in his therapy rooms and secretly recorded sessions for research, which today we would know that's very unethical, but that's what he did. So maybe another predictor of client well-being is, to what extent does a therapist express positive regard? And then maybe a third predictor would be the client's, say, the personality trait of having agreeableness. That is, are you someone who tends to want to be agreeable and get along with others, and you're cooperative, and if people ask you to do things, you're likely to do what other people want you to do because you don't really want to have conflict. You want to be compatible and agreeable with other people. And that's sometimes considered a personality trait of having agreeableness. And maybe clients who have high levels of agreeableness might be more cooperative during therapy sessions, might be more likely to do what the therapist asks, and as a result, they might do better in therapy and have better client well-being at the end of therapy. So we can ask the question, to what degree is client well-being predicted by all three of these things? Alliance, therapist positive regard, and client agreeableness. Now, one of the questions, just to give you a sense of where we're going with all this, is that if you look at those three variables, we might ask questions about, are these all distinct, different things, or is there some overlap between it? For example, if a therapist expresses positive regard, will that necessarily mean the client feels a good alliance? Are these two different things, or are they really two ways of measuring the same thing? And if they're two different things, then I might get a distinct effect for each one. Each one might have a unique effect in explaining variance in client well-being. But if they're two measures of the same thing, if people experience alliance because their therapist expresses positive regard, and one therapist expresses positive regard, that leads to high alliance. If those are actually really the same thing, and when I assess alliance, if I'm not really assessing anything different from positive regard, then if I put those two together, I'm not really adding anything. I don't need to know both alliance and positive regard because they're just two measures of the same thing. So that's a question. Are those two different things? Do they each have a unique, important role in and of themselves in predicting client well-being? Or are they actually redundant with each other? And if I measure one, I'm really measuring the other, and I don't need to include both of those things in my model. So that's one of the things that we'll be looking at as we do multiple regression. And as we look at that, recall in our previous unit, we were talking about the idea of extraction. How can we extract one variable out of another? And that concept is going to become very important here. For example, essentially what we're going to be doing in this unit is asking questions like, what is the effect of alliance with therapist positive regard extracted out of it? What is the effect of therapist positive regard with alliance extracted out of it? And so those are some of the types of questions we can address with multiple regression. Now, many of the things that we will do with multiple regression are essentially the same thing as what we did with simple regression. So up at the top, I have the equation for simple regression, and then underneath it, I have the equation for multiple regression. And note that both equations have a single outcome variable y. They both have a single intercept, and they both have an error. That is how far people's observed scores deviate from predicted scores. The difference is simply, with simple regression, we have one slope and one x. With multiple, we have more than one slope and more than one x. So one important similarity is that with both approaches to regression, both simple and multiple regression, we can talk about what is your observed y and what is your predicted y. So y hat is what gets predicted from the equation. We saw with simple regression, I could just put a hat over y and scribble off the e and say your predicted y is equal to the intercept plus slope times x. We can do the same thing with multiple regression. I could put a hat over the y and scribble out the e and say your predicted y is equal to the intercept plus slope 1 times x1 plus slope 2 times x2 plus slope 3 times x3, which is what I have right down here. Predicted y is equal to that linear equation. And if I have predicted y, I could then compare what is the difference between observed y and predicted y, and that is my error. So the error, if I take the actual y, your actual observed y, your score on the outcome variable that you actually got, minus the predicted y, your score on the outcome that's predicted by the equation, that's the error. And note, again, both equations have error at the end, unless that's assuming we don't have a hat over the y. So if there's no hat over the y, then both equations have an error at the end. Or for both equations, I could put a hat on the y, and that would eliminate the error. And in both equations, the error is observed y minus predicted y. So another thing that is similar between simple regression and multiple regression is that we can calculate the sum of the squared error. That is, we can have a sample of people, and each person in our sample will have an observed score on an outcome variable y, and then we can plug in our regression equation and calculate each person's predicted score on y hat, and then take observed minus predicted, y minus y hat, to get that person's error. And then we can square each person's error, and then sum that up across all the people in our sample, and we will have the sum of the squared error for our study. And that sum of the squared error is important because we use that in calculating intercepts and slopes. Recall from our previous unit that I said we wanted to calculate an intercept and a slope that would minimize our sum of the squared error, that would make that error as small as possible. And I gave you formulas that you could use to calculate an intercept and a slope that would do precisely that, that would minimize the sum of the squared error. For example, if you recall, the formula for a slope was a covariance divided by the variance of x. So now with multiple regression, we need to calculate a single intercept, just as with simple regression, but we need to calculate more than one slope. We need to calculate several slopes. We need to calculate a slope for each predictor. So if I have 3 different predictors, if I have 3 different x variables in an equation, then I will need to calculate 3 different slopes, one for each predictor. And to do that, we will actually take the equations that we used in our previous unit and do a matrix algebra version of those same equations. Hopefully I'm not going to disappoint you, but I'm going to kind of skip over how we use those equations here because it would take a little while to talk about the matrix algebra, and I want to save time for other things. So if you want to learn about the matrix algebra approach to calculating these equations, you could take one of my graduate courses. We get into it there. But for right now, let's skip that part and just know that when you do multiple regression, the computer will do this for you. It will calculate, it will use matrix algebra and calculate an intercept, and it will calculate a slope for each predictor. And the formula it gives you, or the result it gives you, the equation, the intercept and the slopes that it gives you, are intercepts and slopes that will minimize the sum of the squared errors. And yet one more thing that is similar between simple regression and multiple regression is that we can calculate the standard error of estimate. Recall from that googly-eyed sheep table, the standard error of estimate tells us how far people's observed scores typically deviate from the predicted scores. The googly-eyed sheep table, we define distributions by asking the question, observations of what and deviations around what. A standard error of estimate is observations of what? It's observations of different scores from different people. Deviations around what? How far those scores deviate around people's predicted values. That is, y minus y hat. How far do people's observed values, y, typically deviate from predicted values, y hat. And in our previous unit on simple regression, I gave you a formula for calculating the standard error of estimate. And I've just copied and pasted that same formula. This is just a review. This formula here just reviews the formula I gave you in the previous unit, where I said to calculate the standard error of estimate, we take that sum of squared errors that we're just looking at. We divide that by our degrees of freedom to get something we call the mean squared error. And then we take the square root of that to get the standard error of estimate. And we do essentially the same thing to calculate a standard error of estimate in multiple regression. There's just one little difference in our formula, and it's actually just a clarification. When I was doing simple regression, I said your degrees of freedom were n minus 2. Now I want to clarify that actually your degrees of freedom are n minus number of predictors. I have p here, and p means number of predictors. N minus number of predictors minus 1. So note that in simple regression, if I just have one, if I have just one outcome and one predictor, in that case, if I have one predictor, then n minus p minus 1, n minus number of predictors minus 1 equals 2 when I have just one predictor. So this formula I gave you where I said n minus 2 is your degrees of freedom, that's accurate when you're doing simple regression, but when we go to multiple regression, we need to clarify that our degrees of freedom are actually n minus number of predictors minus 1. Otherwise, this is the identical, same exact copy of the identical equation I gave you last time with simple regression. The only difference is I'm simply clarifying degrees of freedom are n minus p minus 1. And with both simple regression and multiple regression, we could calculate a total sums of squares on an outcome variable y. That is, take each person's observed score on y minus the sample mean, how far each person deviates from the mean, and square it, and sum that up to get the total sums of squares. That's the very first step of calculating a standard deviation. So we could calculate that total sums of squares on y, and then we could partition that sums of squares into explained variance sums of squares and error variance sums of squares. And error variance sums of squares is what we were just talking about, y minus y hat squared and summed up. And as before, if we say, for example, take total sums of squares minus error variance sums of squares, that will equal explained variance sums of squares. And all of that will work with both simple regression and multiple regression. And we could plug that into an ANOVA table and do an analysis of variance and calculate an F value. I'm going to talk about that in just a moment. With multiple regression, the F is going to mean something a little bit different than what it did for simple regression. But for now, note that we can do all that same stuff. We can take a total variance sums of squares and partition it into explained variance and error variance, just as we did with simple regression. So one question you may have as we've been going along here is a question of what exactly do we get by doing multiple regression? What does it give us that we wouldn't already get from just doing simple regression? What is the value or benefit or advantage of putting a whole bunch of predictive variables all together in the same equation? What do we get from that? And the key thing is that when we do simple regression, we're limited to addressing just one single type of question. But when we do multiple regression, we can address 3 different types of questions. And those 3 types of questions are listed on the slide here. And this is really the key to understanding everything we're going to be doing in this unit. These 3 questions are really what this unit is all about. We're going to be looking at how multiple regression will allow us to address these 3 different questions. So first we have the question at the very top here. I don't know, what is that, like a green tree frog or something? What is the effect of each x variable ignoring the others? That's essentially the question we've been looking at in our previous unit. That is, if we just look at one predictor at a time and do equations that don't include other predictors in them, that is, ignoring the other predictors, what types of results do we get? So our previous unit on simple regression was essentially addressing that question. What is the effect of each x variable ignoring the others? And we will still look at that question in this unit. That's still an important question, but we're going to expand on that and ask two other types of questions. So another question we can address with this big, what's that, happy orange frog? At least I don't know. I don't know much about frog emotions, but that frog looks kind of happy to me, so I will call it a happy orange frog. What is the total effect of all my x's, all my predictor variables taken together? So if I have three predictors, say, for example, I'm predicting a client's well-being at the end of therapy, and I'm predicting client well-being based on the therapeutic alliance, the therapist's expression of positive regard, and the extent to which the client has an agreeable personality. If I'm using those three predictors, if I take all three of those predictors taken together, how much do they explain variance in the outcome that I'm looking at? In this case, the client's well-being. So what is the total effect of all my predictors, of all my x variables taken together? That's another question we will look at in this unit. And then the third question, which is actually the question we will spend the most time on, with this, I guess that frog is meditating or something over here. What is the effect of each x variable controlling for the others? This is going to bring up that same topic we talked about in our last unit of extraction. If I extract one variable out of another, what is the extent to which one variable has a unique effect on an outcome controlling for other variables in the equation? And we're going to look at how results from multiple regression will give us results that answer this question. What is the effect of each x variable controlling for the other predictors that are in our equation? So a good way to illustrate the difference between these three questions is to use something called a Venn diagram. I don't know, I think many years ago there was someone named Venn who had the idea of drawing an illustration that involved overlapping circles. Everyone thought it was such a wonderful idea that they named it after him. And so today, when we draw illustrations with overlapping circles, we call them Venn diagrams. At least that's my best guess as to why we call it that. So here I have a Venn diagram illustrating an equation, a multiple regression equation with just two predictors. So I'm not using three now. I've dropped down to just two predictors to simplify things just a bit. So I have an outcome variable y, and I have two predictors. x1 is my first predictor variable, and x2 is my second predictor variable. So I have three variables altogether, y, x1, and x2. And I illustrate each variable with a circle. So right here, this circle in the upper right-hand corner, that's the circle for x1. And then on the left, I have the circle that represents y. And then the bottom, I have the circle for x2. So I've got one circle for each variable. And the circle can be thought of as representing the variance for that variable. That is the squared standard deviation. If I wanted to, I could get fancy and I could draw some circles bigger and some smaller, and I draw bigger circles for variables that had larger variances. That is, if their squared standard deviation was a large value, I draw a large circle. And if the variance was a small value, then I draw a small circle. But for this, it's helpful just to make the variances all the same, as if we say we'd standardized all our variables so they all have the same variance. So the size of the circle indicates the variance of the variable, and then the extent to which variables overlap indicates the extent to which one variable explains variance in another. It's the explained variance. And so, for example, let's look at, let's start with the frog in the upper right-hand corner. That was the frog I had for the question of what is the effect of one x on a y variable ignoring the other x variables. So we could say, what's the effect of x1 on y, just ignoring x2. We're not going to pay any attention to x2 right now. And so I have, here's the circle for x1, and here's the circle for y, and the extent to which they overlap indicates the size of the correlation, or the size of the covariance, or specifically here, the extent to which variance in y is explained by x1. So we could say that this area right here area A and D, that's the unexplained variance, like the sum of the squared error. And B and C, that's the explained variance. That's the part of y that's explained by x1. And so if we want to ask the question, what is the effect of x1 on y, just ignoring the other variables, that's the question of what's the effect of a variable, ignoring the others, we want to look at area B and C, this area right here. That's the overlap between x1 and y, and that tells us about the size of the relationship, about the size of the explained variance when I use x1 to predict y, and I'm not thinking about, not paying attention to any other x variables that might be in my equation. So I've just got one variable, one outcome, what's the size of the explained variance, and I can represent that in my Venn diagram. We're looking at area BC. Note that we could do the same thing with x2. If I wanted to say what's the effect of x2 on y, just ignoring x1, that would be area D and C would give me that effect. So B and C, that's the area that answers the question about what's the effect of x1 on y, ignoring the other variables. See how that's slightly different if we go down to this frog right here. That's the frog asking the question, what is the effect of all the variables taken together? How much does both, if we put both x1 and x2 together, how much variance do they explain in y? And this area right here, B, C, and D, all taken together, that's the total effect of x1 and 2 taken together. That's how much variance they explain in y when I consider those variables together. Note that in looking at that total effect, it's not simply, we can't simply sum together how much variance is explained by x1 and how much variance is explained by x2, because our two variables overlap a bit. They're not explaining totally separate things. And so the total variance explained by all our variables taken together isn't a mere sum of how much each variable explains by itself. That's because there's some overlap between our variables. So the key thing is the question, what is the effect of all our variables taken together? When I look at the Venn diagram, area B, C, and D, that's the explained variance. That's the variance that's explained by our two predictor variables taken together. And variable A, or area A, that would be the area that's not explained, our error variance, the stuff that's not explained. And then finally, let's consider our question of what is the effect of each variable controlling for the others. For example, what is the effect of x1 on y controlling for x2? So with this question, we're going to draw in that idea of extraction. What we want to do is extract x2 out of everything. So maybe I'm going to draw lines here. Say I'm going to extract that out. I'm going to take this away and pull it out so it's gone. And so once I've extracted x2 out of everything, and when I say extraction, that's the same thing as saying controlling for or holding constant. So I can say, what's the effect of x1 on y? Controlling for x2. What's the effect of x1 on y? Holding constant x2. What's the effect of x1 on y? Having x2 extracted out. Those are all ways of saying the same thing. So in this case, once I've extracted x2 out of everything, what I'm left with is this part up here. So let me, here we go, I'll put that in yellow. So this is the yellow part, that's what's left over. This part up here is the part that's left over after x2 has been extracted out. After we've controlled for x2, this yellow part is everything that's left over. So now when I'm looking at just that yellow part, to what degree does x1 explain variance in y, controlling for x2? Well, now all I have is this area B right here. That's the overlap between the unique part of x1. The yellow is the unique part of x1. So the yellow is the unique part of x1 and y, the part that's left over after x2 has been extracted out. And so if I'm looking at just that yellow area, to what extent does x1 explain variance in y? Well, B is the extent to which there's overlap between the uniqueness of x1 and the uniqueness of y after x2 has been extracted out. So area B will answer that question, to what degree does x1 explain variance in y after controlling for x2? And note that we could do the same thing for x2. We could say, to what extent does x2 explain variance in y, controlling for x1? In that case, we take all this out. X1 would extract everything out that can be explained by x1. In that case, area D would give us the extent to which x2 explains variance in y after controlling for x1. So that could be B, or it could be D, is another way of illustrating the same question. So that is how we can use a Venn diagram to illustrate our three questions that we can address with multiple regression. So now let's look at how we can answer each of those three questions. And to answer each question, you will need to know two things. First of all, you will need to know what effect size will answer that question. What statistic can you calculate will give you an effect size that will answer the question you're trying to address. Second, you will need to know an inferential statistic. What inferential statistic can you calculate, can you use to determine the significance of that effect, to determine whether or not you could reject the null hypothesis and claim your results are significant. And as we go through this unit, keep in mind that it will be organized by this basic idea of we have three questions, and to answer each of those three questions, we need to know an effect size, and we need to know an inferential statistic to answer that question. And as it turns out, many of the statistics we'll be using here are the same ones we talked about in our previous unit on simple regression. One difference, though, is that with simple regressions, a lot of the statistics were doing the same thing. They were kind of redundant with each other. For example, a correlation and a beta weight, and if we squared our correlation, those were all essentially giving us the same information about the magnitude of relationship between one x and one y. In this unit, these statistics are going to be doing different things. The correlation, the beta, and if we calculate a total percent of variance explained, these are all going to be doing different things. In fact, each one of those things will answer a different question, as you will see as we go through this unit. So let's go through each of those three questions, and for each question, think about, or want to know, what is the statistic that will give us an effect size to answer that question, and what is the statistic that will be an inferential statistic that will allow us to test significance to address that question. So first, let's start with the question of what is the effect of each x variable ignoring all the others. And this is essentially the question we were really looking at in our previous unit. When we do simple regression with just one predictor and one outcome, that is the question we're addressing. We're addressing the question of what is the effect of that x on this particular outcome without any other variables in my equation. In other words, ignoring the other possible predictors that might be there. And we can estimate that effect with a correlation. This is the same correlation we talked about in our previous unit. Recall that a correlation is simply a covariance divided by the average variance of our x and y variables. And we calculate that average variance by taking a geometric mean. We take the product of our two standard deviations to get an average variance. So covariance divided by average variance gives us a correlation. And I note at the top here, I'm calling this a standardized effect. And I do that here because I'm going to be using the word standardized throughout this unit. And I just want to remind you that a correlation is essentially a standardized effect. That is, I can call something standardized if it's a statistic that's based on variables that have been turned to z-scores prior to analysis. And a standardized statistic will always have the same scale. So a correlation will always be on a scale from 0 to +1 or 0 to -1. And recall that if you turn all the variables to z-scores prior to analysis, then your correlation and your covariance are the same thing. So we can say that a correlation is a standardized covariance. So it makes sense to say that a correlation is a standardized statistic. It will always have the same scale, and it is essentially based on variables that have been turned to z-scores. So the basic correlation, the same correlation we've been talking about all along, will give us that standardized effect of each x variable on y, ignoring all the other predictors. The effect of each predictor, or a single predictor by itself. How much does x explain variance in y? Ignoring any other potential x variables we may have in our analysis. So that's what the correlation does for us. And the correlation gives us the effect size. So the correlation will tell us what is the magnitude of effect between x and y without considering any other predictors. So going back to our Venn diagrams, we can represent what a correlation does using a Venn diagram. So let's start with a squared correlation, which is the percent of variance explained. What is a percent of variance in y that is explained by x1, ignoring other predictors, say, for example, ignoring x2? Well, the total variance in y is this full circle A, B, C, D. That's the total variance in y. And the variance that's explained is the purple area, the BC area. So if I take area BC, that's the part of y that's explained by x1, divided by ABCD, that's the total variance of y. Recall that that's the formula for explained variance, or percent of variance explained. If I take explained variance divided by total variance, that gives me the percent of variance explained. Area BC represents the area of explained variance. ABCD represents the total variance in y. So we can say area B plus C divided by A plus B plus C plus D is explained variance divided by total variance, and that is the percent of variance explained. And recall that the percent of variance explained is r squared. If we take a correlation and square it, that gives us the percent of variance explained. And so then if I simply take the square root of that, which I've done over here on the right, the square root of my r squared is simply r not squared. Unsquared r, just regular lowercase r, is the correlation between x1 and y, and we can represent that as the square root of area B plus C divided by area A plus B plus C plus D, the total variance. Explained variance divided by total, take the square root of that, you have your regular ordinary correlation. Now, one thing that will be important to note here is that I am illustrating these correlations with lowercase r. And in a moment here, I'm going to talk about an uppercase r, which will be something different. So it's very important to note that if I'm talking about the effect of one x variable on y, ignoring the other predictors, the effect of one variable by itself, ignoring the other predictors, if I'm asking that question, to what extent does x1 explain variance in y, ignoring x2, then that our effect size is going to be lowercase r, or r squared. Now, when we're doing this, usually it's going to be more common to report our correlation as unsquared, as just a regular correlation. To square, our correlations are going to be less common, but either one would answer that same basic question. The important thing is to note that when I talk about the effect size, the magnitude of relationship between x1 and y, ignoring x2, or ignoring other predictors, we get that information from our lowercase r. I'll call that just a bivariate correlation. Bivariate meaning just two variables. So a bivariate correlation, a correlation between two variables, is indicated by the lowercase r, and that answers the question of what is the effect of x1 on y, ignoring the other predictors. And we could do the regular correlation by itself, or we could square it. Either way would address that question, although more commonly we don't square it for this question. So if the lowercase r, the simple bivariate correlation, is the effect size, giving us the relationship between x and y, ignoring the other predictors, how do we test the significance of that correlation? Well, we've already talked about that. We can test significance of a correlation with a t-test. And this is just review from our previous unit. Here is the formula for a t. As always, a t-test is a statistic divided by its standard error. So here we have the correlation divided by the standard error of the correlation. And with any t-test, I say the t is a statistic divided by its standard error. And you say, well, is there a formula I can use to calculate my standard error? And I say, yes, it is. Yes, there is. And over here we have our formula for the standard error. And again, this is just review. We've seen these. This is the same formula I gave you in the previous unit. We take the square root of 1 minus r squared divided by n minus 2. And that will give us our standard error of the correlation. That is, if we do our study over and over again, how much will our correlation that we observe in our studies typically deviate from the true population parameter? How far do our statistics typically deviate from the true population parameter? It's a measure of sampling error. So the standard error of the correlation tells us how far our correlations typically deviate from the true population parameter if we do our study over and over and over again. And if we take our statistic that we got in our study, the correlation we got from our study, divided by its standard error, we will have a t-value. And again, once we have a t-value, as we've always done in the past, we can determine the significance of our statistic. We can determine the significance of our result. We can use a t-table or a t-calculator to determine what is the probability of this t-value, assuming the null hypothesis is true. We can do that because the t is a mathematically defined distribution, and we know the exact shape of that distribution if the null hypothesis is true. If you wanted to, you could use calculus to calculate your own t-values, but we always, at least I always typically just look them up or use a calculator or use a t-table. And when you look up a t-value, we always need to know degrees of freedom because a t will change shape just slightly depending on your degrees of freedom. So to get the probability of a t-value, we need to know what is your t-value and what are your degrees of freedom. And in this case, our degrees of freedom are going to be n minus 2. Again, this is the same thing we looked at in our previous unit. I'm not telling you anything new here. So n minus 2 degrees of freedom. Once you have your degrees of freedom, t-value, you can determine the significance of your correlation. So now you know how you would answer that question. What is the effect of each x variable on an outcome variable y, ignoring the other predictors? What is the effect size? You test the effect size with a correlation. What is the inferential statistic you use to test the significance of your effect size? You test the significance of the correlation with the t-test. And that will answer the question, what is the effect of an x variable on a y variable, ignoring or not paying attention to or not using the other possible predictors? So this slide is just giving further clarification about exactly what a multiple correlation is. If I have a capital R or capital R squared, what exactly is that? So like I was saying, capital R is something I call my multiple correlation. So what exactly is a multiple correlation? One way of understanding a multiple correlation is that it is the correlation between observed y and predicted y. Let me go back to a previous slide where I have my regression equation on it. Let's see, here we go. So here we have our regression equation, and recall that we can, if we're trying to predict someone's score on y, we have y hat, and we have our predictors here. And then if our predictors work really well, if our x variables are strongly related to our outcome y, say, for example, we're trying to predict client well-being, and we're trying to predict client well-being using measures of how much people have a strong alliance with their therapist, how much the therapist expresses positive regard, and how much the client has a personality type of agreeableness. And if those three things do a very, very good job of predicting outcomes, if they are strongly related to the outcome, if there's a really strong relationship, then we can very accurately predict people's well-being based on those three predictors. And in that case, we will have a very small error. So if there's a strong relationship between our x variables and our y, then our error will be small. Observed minus predicted will be very small. In contrast, if my variables don't do a very good job at all, if really well-being is predicted by other things, and my predictors in my equation, maybe the alliance and the agreeableness and the positive regard, maybe they really didn't do much at all in predicting a client's well-being. They really aren't that important after all. And in that case, we'd have large error. Every person, their observed score would be quite a bit different from their predicted score. We'd do a terrible job of predicting people's scores. So when we look at this error, it's giving us information about what is the size of relationship between our predictor and our outcome. And we saw that in our previous unit when we were talking about explained variance, that when our error is big, our explained variance is small, we have a weak relationship. When our error is small, then we have a strong relationship and our explained variance is large. And that we've been looking at that before. Now note, another way we could talk about the size of this error is to say, what is the correlation between your observed y and predicted y? So rather than saying observed minus predicted, we can say, what is the correlation between observed y and predicted y? Because if I do a study and I say I have a sample of people and everyone completes a measure of, say I'm doing my study of people who are receiving therapy for depression. And so I have a score for every single person in my sample about their level of well-being. and I've assessed the alliance, and I've assessed the therapist's positive regard for each person, and I've assessed each person's personality type of agreeableness. And then once I've collected all my data, I get my regression equation that will have an intercept and a slope times x1, slope times x2, slope, and I plug that in. And for every single person, I will get that person's predicted score on y. And so now in my data set, every single person has an observed score on y, what their actual level of well-being was at the end of therapy, and every single person has a predicted score on y, which is the score I predicted based on my regression equation. So I could simply calculate what is the correlation between observed and predicted y. So again, rather than taking observed minus predicted, we could calculate the correlation. That is, we could calculate, we have two variables, observed y, predicted y, calculate the covariance between those two variables, calculate the standard deviation of y, the standard deviation of predicted y, and take our covariance divided by the product of our two standard deviations, and we'd have a correlation. And note that that correlation also will tell us about the size of the error. Because if our variables do a really, really good job predicting y, if we have a really strong relationship, if we have a lot of explained variance, then observed y and predicted y will be nearly the same thing. In other words, there will be a high correlation. And if our variables are actually perfect, if we actually have a set of variables that perfectly predict y, if there's a perfect relationship, then we'd have a perfect positive correlation. We'd have if our observed variables perfectly predict y, then our correlation would be 1. On the other hand, if our variables don't do a good job of predicting y, then we'd have a great big difference, that your observed y and predicted y would be very different from each other. And in that case, we'd have a weak correlation. So there's two ways that we could talk about the effect size here. We could talk about the error, observed minus predicted, and that gives us some indication about an effect size. Or we could simply talk about what is the correlation between observed y and predicted y. And we can do that, and we can calculate that, and when we do, that calculation is the multiple correlation. That's what we get when we calculate a multiple correlation, is we're actually getting what is the correlation between observed y and predicted y. So that is a second way of understanding what a multiple correlation is. Let me, whoops, went too far, way back here. Here we go. And so here's the slide we started with here. Let's look at one third way that we can talk about this. And if we take our multiple correlation, which is the correlation between observed y and predicted y, and we square that, and we get the capital R squared, that is going to say, that's going to give us what is the total amount of variance in y that is explained by all the variables combined together. So we can use a language percent of variance explained if we square our multiple correlation. And the percent of variance explained by all the variables taken together, that's what we get by R squared. Capital R squared, the squared multiple correlation, is the percent of variance explained by all the x variables combined together. So those are three different ways of defining what I mean by capital R or R squared. So we could calculate a multiple correlation and a squared multiple correlation, that is capital R and capital R squared, by simply taking the correlation between observed y and predicted y, and that correlation is your multiple correlation. And if you take that correlation and square it, you will have your squared multiple correlation, capital R squared, or the percent of variance explained. But a much easier way to calculate these values is to go the reverse direction and to start by partitioning your variance, your sums of squares, into explained variance sums of squares and total variance sums of squares. And from that, calculating your percent of variance explained, capital R squared. And then if you want to get a multiple correlation that's not squared, simply take the square root of capital R squared. And this is a much easier way to go because we can get all the values you need for calculating this from an ANOVA table, from doing an analysis of variance and getting your values from this table. I mentioned a moment ago that we can use this exact same table both when doing simple regression and multiple regression. And we can get all the values we need for calculating percent of variance explained from the sums of squares column. In a moment, we'll go on and talk about how we can use the rest of this table to calculate an F value for doing a significance test. But for right now, let's just focus on this sums of squares column. Recall that we can calculate a total variance sums of squares, and this would be the sums of squares for the outcome variable y in our equation, which is y minus the mean squared and summed up for every single person in our sample. And then we can calculate our error variance sums of squares, that is observed minus predicted, y minus y hat squared and summed up for everyone in our sample. And then we can take our total variance sums of squares minus our error variance sums of squares to get the explained variance sums of squares. So again, explained variance sums of squares divided by total variance sums of squares gives us the percent of variance explained, which is our capital R squared. Now, recall that we did the exact same thing in our previous unit when we were talking about simple regression with one predictor and one outcome. We had this ANOVA table. We did an analysis of variance, and we partitioned our variance into explained variance sums of squares and total variance sums of squares, and we took explained divided by total to calculate the percent of variance explained. But note that in our previous unit with simple regression, this procedure answers a different question. When I'm doing simple regression, I have just one predictor, and so when I use this procedure to calculate percent of variance explained, it gives me the percent of variance explained by just that one predictor. So in other words, in that case, it's answering the question of what is the effect of that one predictor when I'm ignoring all the other possible predictors there could be. Now, when we use this procedure with multiple regression, we're answering a different question. Now, this procedure will answer the question, what is the percent of variance explained by all the predictors taken together? Because I'm doing this in an equation that has multiple predictors. So it will give me the percent of variance explained by all those predictors taken together. So with multiple regression, doing the analysis of variance table and calculating the percent of variance explained gives me now capital R squared, a multiple correlation, the percent of variance explained by all my variables taken together. And then if I take the square root of that, that will give me the unsquared version, just the multiple correlation, not squared. One thing to note is that these values, capital R squared and capital R, cannot be negative. That is, you cannot have negative explained variance. You can explain zero variance, you can explain some variance, but you can't explain negative variance. In other words, the correlation between observed y and predicted y cannot be a negative correlation. When you have an x variable trying to predict y, that x variable might make your prediction better than just, say, guessing by random chance or guessing the mean score for every person in your sample. But a predictor variable cannot make your prediction worse. You cannot have a situation by using a predictor you predict worse than you would if you had no predictor. Predictors can be useless or they can be beneficial, but they can't be detrimental to making predictions. So you can't explain negative variance, which means capital R squared and capital R are values that can never be negative. So one thing that happens with a multiple correlation or a multiple correlation squared, and this actually is true for both the capital R squared and the lower R squared, is that these are all statistics that cannot take on negative values, and because they cannot take on negative values, these statistics are actually biased. So what do I mean by bias? Recall way back we gave a definition for bias, that a bias is when the expected value for a statistic is not equal to the true population parameter. That is, if I do a study, calculate my statistic, replicate my study, calculate my statistic, replicate my study, calculate my statistic, and if I do that an infinite number of times, and then take the average of all my statistics across all my studies, that average is my expected value. And most of the statistics that we talk about in this class are unbiased. unbiased statistics. And what that means is that the expected value is the same thing as the population parameter. If I replicate my study over and over and over again an infinite number of times, the average of all my statistics across all my studies will be equal to my true population parameter. And that is true for most of the statistics that we talk about in this class. Most of them are unbiased, meaning that the expected value is equal to the true population parameter. But that is not true for the capital R squared, or the lowercase r squared, the multiple correlation or any correlation squared. And that's because these correlations cannot take on negative values. So to illustrate where this bias comes from and what I mean by this, I have an example here. Say I wanted to do a study and I was going to calculate the correlation between people's big toe sizes and intelligence, which I guess that's a picture of a big toe down here. So maybe I had some way of measuring the size of people's big toes, and I had some kind of so-called intelligence test, and I measured everyone. I had a sample of people, and maybe I have study 1. And I measure everyone's big toe, and I give them some kind of intelligence test, and I get the correlation between big toe size and intelligence. Now for this example, let's assume that the null hypothesis is actually true. That in this case, maybe there's actually no correlation whatsoever between the size of your toe and your intelligence. So let's assume the null hypothesis is true and that the true population parameter is 0. Now, of course, when I do my study, I'm not going to get exactly 0 in my study. So say I do study 1, and I get a very, very tiny, itsy-bitsy positive correlation of 0.05. And then I do study 2. I replicate my study, and this time this time it's negative, a negative small correlation, a negative 0.1. And then I do study 3, and this time now my correlation's positive, and it's positive 0.2. And then study 4, I get a negative 0.05. Notice what is happening here is that if the true population parameter is 0, I would expect sometimes to get positive correlations and sometimes to get negative correlations. All the time they're going to be very, very small correlations because the true parameter is 0. So in my studies, I'm likely to get correlations that are very close to 0. Not exactly 0, but very close to 0, sometimes positive and sometimes negative. So if I average across, say, these 6 studies, 0.05 plus negative 0.1 plus positive 0.2 plus negative 0.05 plus positive 0.1 plus negative 0.2 divided by 6, my average comes out to 0. And if the true population parameter was 0, this would be true if I replicated my study over and over and over and over again an infinite number of times. If I replicate my study an infinite number of times, the average of all my correlations across all my studies will equal the true population parameter. And if the true population parameter is 0, that's what the average of all my correlations will be. And we could show mathematically we could prove that will always be true for the lowercase correlation not squared. And so what I'm showing you is that the lowercase bivariate correlation not squared is an unbiased statistic. It is not biased. The expected value, the average of all my studies, will equal the true population parameter. But note that once I square my statistic, it can no longer take on negative values, and now the average of all my studies is not equal to 0. And if that 0 was the true population parameter, it would show that it's not equal to the true population parameter. So if the null hypothesis was true and the true population parameter was 0, and I got this result here. So here I have study 1. My correlation was 0.05, and I square that, and 0.05 squared is 0.0025. Study 2, I got a negative correlation, negative 0.1. Square that, I get positive 0.01. Study 3, I got a correlation of 0.2. Square that, I get positive 0.04. Study 4, I got a correlation of negative 0.05. I square that, I get positive 0.0025. So when I square my correlations, every effect is positive regardless of direction. They're all positive squared values. And so if I average all these positive squared values, my average is not going to be 0. And what I'm illustrating in my example here was supposed to be a situation where the null hypothesis was true, and this would show that even though the null hypothesis was true, the true population parameter was 0, the average of all my studies of all their squared correlations cannot possibly be 0, because every time I square an effect, I will always get a positive value, and the average of a whole bunch of positive values will always be a non-zero positive value. And this would be true even if the null hypothesis was not true. This example is easy to illustrate if we assume the null hypothesis was true, but even if the true population effect was some non-zero value, maybe the true correlation was 0.2 or 0.3, what will always happen is that these squared values, or the capital R squared, lowercase r squared, these values that cannot take on negative values, they will always be biased upwards. They will always give you an estimate that is a little bit larger than the true population parameter. So that's the key take-home message here, is that capital R squared, and lowercase r squared cannot take on negative values. Therefore, they are biased. They will give us estimates that are always going to be, on average, a slight overestimate of what the true population parameter is. One thing I'm not going to get into too much for this class, but I want to make you aware of, is that there are formulas that you can use to try to correct for that bias. They don't always do it perfectly, but they can come pretty close. And so there is something called an adjusted r squared, which is an estimate of r squared adjusted for the bias. It's trying to take that bias out and give a good estimate of what do we think r squared would have been if it wasn't biased. So that's what adjusted r squared is, an estimate of r squared without the bias. It doesn't perfectly remove it, but it comes pretty close. So finally, let's look at how we can represent a multiple correlation or multiple correlation squared using the Venn diagrams. So our capital R squared, our squared multiple correlation, that's the total percent of variance explained in Y given all of our predictors taken together. So we can represent that as area B plus C plus D. That's that green area up here, which is all the area explained by x1 and x2 taken together, divided by area A plus B plus C plus D. That's our total variance in Y. So if I take the explained variance, the part of Y that's explained by x1 and x2, which is area B plus C plus D, divided by the total variance of Y, A plus B plus C plus A plus B plus C plus D, that gives us our percent of variance explained. That is the total percent of variance in Y explained by all the predictors taken together, which is our capital R squared. And if I take the square root of that, I will have my capital R not squared, my multiple correlation not squared. And so that is how we can represent the capital R squared, or capital R, that is the multiple correlation squared, or multiple correlation not squared, with a Venn diagram. So if I want to answer the question of this big happy orange frog, the question, what is the effect of all my x variables taken together in predicting an outcome, my effect size is the capital R squared. The squared multiple correlation answers that question. What is the total amount of variance explained by all my variables taken together, all my x variables, all my predictors taken together? And we could answer that question both with a capital R squared or the capital R not squared, but it is actually much, much more common to report the capital R squared version for the question, what is the effect of all my x variables taken together? So if capital R squared is my effect size, how do I test the significance of that effect? What is the inferential statistic that I will use to test the significance of capital R squared? I will test the significance of my capital R squared with an F test. The F test will be the significance test. It will be the inferential statistic we will use to test the significance of R squared multiple correlation. And we calculate an F value by doing an analysis of variance, doing an ANOVA. And we saw before throughout this unit how we can plug the values into this ANOVA table and how it is just the same as the ANOVA table we looked at in our previous unit with simple regression. So we can calculate our total variance sums of squares, our error variance sums of squares, and our explained variance sums of squares. And now we can go ahead and complete the rest of this table. One thing to note is that in our previous unit, we didn't really need to pay attention to the number of predictors because the number of predictors was just one. With simple regression, with one predictor and one outcome, the number of predictors is always just one. But now, with multiple regression, you do need to pay attention to exactly how many predictors do you have. So your explained variance degrees of freedom is number of predictors. Your error variance degrees of freedom is n minus number of predictors minus 1, and your total variance degrees of freedom is n minus 1. And then at this point, you can take your explained variance sums of squares divided by degrees of freedom to get your mean squared explained. You can take your error variance sums of squares divided by degrees of freedom to get mean squared error. And by the way, just to review, what you get if you take the square root of your mean squared error. Recall that the square root of your mean squared error is the standard error of estimate. That is, the average distance that people's observed scores deviate from their predicted scores. And whether you're doing simple regression or multiple regression, the square root of your mean squared error is always your standard error of estimate. So anyway, now you can proceed to take your mean squared explained variance divided by mean squared error. Mean squared explained divided by mean squared error will give you your F value, your F statistic. And the F statistic is a test statistic. Just like a t-value, it has a known distribution if the null hypothesis is true. So you can calculate an F value and then determine the probability of that F value if the null hypothesis is true. And if your probability is less than 0.05, you reject the null hypothesis and decide that your results are significant. And if it's not less than 0.05, your results are not significant. And to determine the probability of your F value, you can look it up on a table, or use an online calculator, or use a computer program, or do the calculus yourself. Regardless of how you do it, to determine the probability of F, you need to know what your F value is, and you need to know your degrees of freedom, and in this case, we need to know degrees of freedom numerator, the degrees of freedom for your explained variance, which is number of predictors, and degrees of freedom denominator, your degrees of freedom for your error sums of squares, n minus p minus 1. So if you know your F statistic, your degrees of freedom numerator, degrees of freedom denominator, you can then determine the probability value, that is, the probability of getting this particular F value if the null hypothesis were true. And if that probability is less than 0.05, your results are significant. In other words, you can say you have a significant multiple correlation, or a significant R squared. Note that this is another situation where we're doing the exact same procedure that we did in our previous unit on simple regression, but now this procedure is answering a different question. In our previous unit on simple regression, we looked at 3 different ways of doing significance tests. We looked at 3 different types of inferential statistics we could use. In our previous unit, we calculated a t-value for a correlation. That was a t-value for a simple bivariate correlation between one x variable and one y. And we calculated a t-value for a beta weight. And then we also calculated an F statistic. And in our previous unit, all 3 of those different significance tests were testing the exact same thing. They were testing the association between a single predictor and an outcome. But now, in this current unit on multiple regression, each one of those significance tests, each one of those different ways of doing an inferential statistic is going to answer a different question. So as we saw a little while ago, if we calculate the simple bivariate correlation, we can do a t-test to test the significance of that correlation, and that's an inferential statistic. That t-test for your bivariate correlation is an inferential statistic that answers the question, what is the effect of a single x variable on an outcome, ignoring all the other possible predictors? Now, if we want to answer the question, what is the effect of all the variables taken together in predicting that outcome, the inferential statistic will be the f-test from the ANOVA. And now the f-test will answer the question of what is the effect of all the variables taken together, and it doesn't answer the other questions. And the t-test for the simple bivariate correlation will answer the question of what is the effect of a single x variable predicting an outcome, ignoring all the others. So each one of these different significance tests, each one of these different approaches to doing an inferential statistic will answer a different question in this current unit on multiple regression. So one thing that will help you keep track of different inferential statistics, and specifically one thing that will guide you in knowing when to do a t-test and when to do an f-test, is to keep in mind the distinction between a focused question and an omnibus question. I've mentioned those terms before. Recall that a focused question is a question you can address with two hands. For example, what is the correlation between x and y? What is the correlation between two variables? So that very first question we addressed in this unit, that question of that green tree frog, of what is the effect of a single x variable on an outcome, ignoring all the possible other predictors, that is a focused question. It's looking at a simple correlation between two variables, and a simple correlation, a simple bivariate correlation, is a focused question. In contrast, our big happy orange frog here is asking an omnibus question. What is the effect of multiple predictor variables taken together in explaining variance in an outcome? That is a question that requires more than two hands to hold all those variables. So it's an omnibus question. So in doing significance testing, when I want to do an inferential statistic to calculate the significance of a result, I will always use a t-test if it's a focused question, and I will use an f-statistic if it's an omnibus question. That's because a t-test is limited. A t-test can only test a focused question, and it's not capable of testing the significance of an omnibus question, whereas an f-statistic is capable of testing the significance of an omnibus question. So when I'm doing multiple regression, the f-statistic is the one that will address this omnibus question. It will calculate the significance of my capital R squared, which is the effect of all the variables taken together. It's the effect of all the predictors taken together in explaining variance in the outcome, which is the omnibus question. That is the question of my big happy orange frog. And that is everything for part A of Unit 5.